Hello everyone. So today we will discuss chapter number 1 of digital media course. I have divided this chapter into 4 parts and today we're going to talk about the first part of chapter number 1. We have 2 agenda items in chapter number 1, part 1. First we will discuss a difference between analog data or analog information versus digital information, and then we're going to talk about a process which is called digitization. In digitization, actually we discuss the processes, how we can convert analog information into a digital data. We have 3 outcomes of this chapter number 1, part 1. We will discuss mainly 3 things. Firstly, we will discuss the analog information. Firstly, we'll discuss the digital data, like digital information. What is basically a digital information is, and I believe everybody is well familiar with the digital data, digital information, because digital information is the one which computers they use to store the data or transmit, or you can say they communicate communicate information or transmit information using a digital format. So digital information is the one which computer uses to store or transmit data or information. Then the second thing that we're going to learn in this chapter is going to be the analog information. Analog information, the role of analog information in our daily life, and we will discuss why we are discussing. I'll just build a rationale, like why we are discussing analog information or analog data in a digital media course. We will talk about it. Last but not the least is we will discuss a process called digitization. We will discuss digitization in detail with some examples so we can understand why analog information is important and how we convert analog information into digital so computers can use it, computer can process it. And we will also discuss why computers always require, or why computers they use a digital data or digital information. So let's start with the first thing, or the first agenda item, difference between analog data and digital data, starting with the analog information. So analog information is basically a continuous information, like information having infinite point. Like for example, something like that, if I just make a graph. For example, this is a graph. And let's say if I just start the time from here, let's say assume that this is basically a puppy's weight growth over the time. This is, let's say, time, and that's basically the weight of a puppy. Assume that that's a puppy's weight. And time is, let's say, in months. For example, 0 when the puppy born, 1 month, 2 months, 3, 4, 5, and over the 6 months, we have measured the weight of puppy, for example. And that's the weight in pound. For example, it's going to be 5 pounds. Let's say this is 10 pounds. It's going to be 15 pound. That's 20 pound. Assume that. Now the thing is, in analog information, like if you see this graph, this is the analog information. Like analog mean between any 2 measurement, let's say from between month 1 and 2. If you see down here, there are infinite points. Like the time could be, let's say, 1.12. Let's say this is 1.12 second or whatever the time is. At that point, we have a information available at 1.13100. So for each and every instant, we have a corresponding value. This is called analog information or continuous information. So analog information is something which is continuous. Continuous information. And other than continuous information, it has, you can see down here, we have infinite point. Like there is a point, there is a time instant 1.1000001, 1.1000003, etc, etc, etc. So we have infinite instances. So we can say here analog information is basically having infinite number of you can say points or divisions, or you can say points between 2 measurements or any 2 instances measurements. So it has infinite number of divisions, and The problem is, since we have, let's say you want to store this graph inside your computer. Computer cannot store this graph as it is. Why? Because computers cannot store infinite information. So to store analog information, store analog information, we need infinite storage. Infinite storage. Why? Because analog information contains infinite points. Infinite information is stored inside the analog information. Like, just take the example of this graph. Other examples could be, for example, temperature or temperature. You can say weight, the weight growth. Then we have time. This is basically etc, etc. These are some of the examples of analog signals or analog information. Temperature, I mean, you can ask, for example, why do we have the 37.5, for example, centigrade, or I mean this point. This is basically, when you see the points and all these things, these are basically digital data. Like, if you, for example, you want to measure a temperature, let's say on an analog thermometer, for example. So analog thermometer, let's say it has different scales. Like, let me just give you an example. Let's say thermometer start from, let's say 97, 98, let's say 99, 100. For example, if your temperature is in between right here, something like that. So what you will, I mean, we approximate it, we say it is, let's say 97.5, but the value could be 97.5001234, or it could be 97.51001100, etc, etc. Are getting the point? So we don't have exact number here. Why? Because it could be infinite, because from 97 to 98 there are infinite possibilities, infinite numbers. I mean, we discretely, or we just we call it from 97 to 98, this is just a one step, or one you can say a one division. But actually between 0 to 1 we have, I mean, if you take example from 0 to 1 or 1 to 2, we have infinite points. Like, mathematically there are infinite values, like 0.1, 0.000001, 0.00000001, etc, etc. But we discard them whenever we make them digital. So let me repeat what we have discussed. Analog information is continuous, like, I mean, something like a graph or something like that. It contains infinite values, infinite number of points between two measurements, and to store analog information, we need infinite storage. Now let's come to the digital one. Digital information is basically having finite, or you can say discrete number of points. Number of points is called digital information. That is digital information. For example, if you want to give an example of discrete numbers, for example, let's say number of questions, okay, number of people in a group, number of students, for example. So something which you can count. This is basically called discrete data, and that's the one which we can store inside a computer, because computer can store only something which is finite. It cannot store all the infinite data, because we don't have infinite storage, by the way. So that is why we convert analog data into a digital information. So let me just give you some more deep understanding about it. So whatever you guys see in the natural world, like whatever you see through your eyes, it contains infinite information. It is a continuous information. Like whatever you guys see, like the colors, whatever the colors that you guys see around in the natural world, it contains infinite colors. So we cannot actually have infinite colors palette. So that is why we need something which is digital, finite, and this is why we convert analog data into digital data. So just to give you an idea, whatever we see in our natural world, is analog. It's not only analog, plus it is continuous And if it is anything which is continuous, it is basically, it contains infinite points. Now the problem, since it is infinite, we cannot store inside the computer, cannot store or cannot handled by computer. So computer cannot handle or store the analog data, analog information. But for example, if you capture a picture in a natural scene or natural world, for example, so the camera is a digital device, it's a computer. So what will happen, that camera, whatever it will capture, it will only capture the finite, or it will only store the finite values. So what does it mean? It means if you capture a picture of something which is analog, so we need to convert this analog thing into digital format, like having discrete values, so computers can store it. So it can be stored inside the computer, or it can be stored inside the camera as well. So typically what we do is we actually approximate the continuous value to a nearby discrete point. So typically we approximate. In our class, I'll just show you a couple of slides, some pictures, PowerPoint, and then you will have a better understanding why there is a difficulty in reading the exact value in an analog thermometer or analog devices. So typically we approximate the continuous value to nearby discrete point. And that nearby discrete point is basically it will turn into a digital value. We'll discuss that. So what we have discussed so far, we have discussed the difference between analog data and digital data. What is analog data? Analog information is something like having infinite points, continuous information which contains infinite divisions, infinite points between any two measurement or any two numbers. The problem with the analog information is it contains infinite data which we cannot store inside our computer. So that is why we need to convert this analog data into a digital format so computers can handle and store the data. Now let's come to the second section, which is digitization. And as we discussed, the definition of digitization is the process of conversion of analog information or analog data into discrete, or you can get digital. Discrete is basically finite values. Digital is like 0, 1, 0, 1. We will discuss that in detail, but just to give you an example, the process of conversion of analog data into discrete or digital data is called digitization. Now, digitization is actually of two steps. There are two steps involved in digitization. The first step of digitization is called sampling, and the second step is called quantization. So there are two steps in digitization. I mean, what I'm trying to say is, for example, this is your analog wave, okay? And you want to convert this analog wave or analog signal. This is your analog or continuous signal having infinite values. Like if you see 0.0001, it got a value. We want to convert this analog signal into a discrete or digital signal. So what we will do is we will pass it through the box, and that box is, for example, where we are doing the digitization. And what we do in digitization, firstly, this signal will pass through the sampling, like something like that. It will pass through the sampling. After sampling, it will pass through the quantization. And after quantization, you will get like a discrete signal, something like that. So you got a discrete value, having finite stuff which we can store inside our computer. Okay. So we are feeding analog signal. After passing through sampling and quantization, we will get discrete values, discrete points. If you join them together, you can get the analog signal back. But discrete is why? Because we want to store it inside our digital devices or computers. All right, so now let's discuss what we do in sampling and what we do in quantization in detail, and with the help of some graphs and some examples. So let's understand sampling. In sampling, what typically we do? In sampling, what we do is we set a sampling rate. So we actually set a sampling rate. And what exactly a sampling rate is? Sampling rate is basically how often we capture or we record or take samples of analog wave or analog signal, analog information. So that's basically called sampling rate. Let's understand it, what exactly it is. So for example, we have, let me give you a simple example. Let's say we got this signal. Assume that this is basically an analog signal. And this signal is, for example, let's divide it. For example, this is time instant 1. And this is, let's say, 2 second, 3 second, 4 second, 5 second. Assume that this is basically over. And let's say, let me just make a big signal. Excuse me. 6 and 7. And for example, it is something like that. Okay. And 8. So I have this analog wave. Analog wave mean it is basically a discrete information. It's a continuous information having infinite points. Okay. Now the problem is, since we cannot store this analog information in a computer, so I need to do the sampling and quantization, which we talked about. We need to do sampling and quantization in order to convert this analog signal into a digital one, into a digital or discrete format. Okay. So firstly, let's see what we do in sampling, and then we will talk about quantization. So let's say this is the signal and I want to do the sampling. And for example, we set a sampling rate. Because we set a sampling rate, assume that we set a sampling rate because this is seconds. So let's say one sample per second. So in 1 second, for each second, we gonna pick one sample. So for example, if we pick one sample in 1 second, so what's gonna happen? What will be the samples? So we'll pick this sample here. In between, for example, in between at 0.5, we pick one sample. 2.5, we got one sample. 3.5, we got this sample, we got this sample, we got this sample, let's say this sample, this sample. So this is basically called sampling, and let me show you the output of sampling. So the output of sampling is going to be, just let me show you the points here. The points, let's say this is 1, that was 2, that was 3, that was 4, 5, 6, 7, 8. If I would like to pick this, show you samples, this is the first sample, this sample, this is the second sample, third sample, fourth sample, fifth one here, this is another one, and that's the other one. If you want to combine them, this is basically how it will look like now. If I just join them together. If you guys see, this is basically the sampled version of this analog wave, which is not exactly what it should be, but very close to that. Now, this is called sampling. Okay. So what we did is we have constructed this signal, like this analog signal, by joining these samples. So what we did is we actually picked the samples rather than processing everything. We just pick the samples in order to construct the information. This is called sampling. So what we do in sampling, we set a sampling rate and then capture the samples out of the sampling wave, and output is something like that. It's not basically, you don't have to combine them. Output is something like that. That's going to be the output, which is, close to the original, but we have missed because analog contains 100% information, and digital always, it has less information as compared to analog. Okay. Because we are missing all this information between all these points. We just pick these samples. This is basically what the sampling is. So we always discard the information in analog in order to make it digitized or digital. Now, for example, if we increase the sampling rate, let's say, rather than picking one sample per second, if I increase here, for example, 3 samples per second. If I pick 3 samples per second, let's see what's going to happen. If I pick 3 samples, let's say in 1 second, 3 samples. This one more, between this. If I'm keep on increasing the samples, I'm going to actually between this 1, 2, 1, 2 more. So I'm basically picking now 3 samples in 1 second. So you guys can see 3 samples per second. And here I'm going to actually pick this one. Here I'm going to pick this one, this, and this. And now you guys can see here, we will have more information, like more samples. And you will see it will be more close to original. It will be more close to original if you pick more samples. You guys can see here, if I construct it back, now it is more close to original. Okay, are you getting my point? So what does it mean? If we increase the sampling rate, automatically result will be better. For example, let's say, just to give you an example, let's say for president elections, let's say we are having our US president's elections. For president election, we have total 32 million population. 320 million population. So we have 320 million population. What do you think? All the people, they vote for president? I mean, they cast their vote in the elections? No. Maximum turnover is approximately 130 million. Maximum. I'm just giving you, or 100 million is the max. Let's say 130 million. So based on 130 million votes, we decide over president. So automatically, for example, if this number will go up, let's say if all the 320 million, or let's say 300 million people, they vote, then it would be true reflection. Are you getting the point? The result will be much better, much closer to original. Exactly the same thing down here. If we have more sampling instants, more samples, if we increase the sampling rate, we will have more accuracy. So sampling, what is sampling? We set a sampling rate, and sampling rate is how often we will capture or pick the samples of analog wave. So the learning points here, 2 points. If we have higher sampling rate, what's going to happen? It would be more close to original, or you can say more close. Original was analog, more close to original, more accurate. But the problem is, if sampling rate is higher, if you increase the sampling rate, the problem is going to be more data. File size will be bigger. File size will be larger. Why? Because what is happening here, we are now having, in the 1 second, we have 3 samples as compared to 3 samples as compared to 1 sample. So if you increase the samples, you have to store more information, more data, file size will be larger. So pros is that it will be close to original. Con is that it will be file size will be larger. Now, if we reduce the sampling rate, lower sampling rate, if you say, let's say, rather than having 3 samples per second, 1 sample is fine. So if we lower the sampling rate, it will be reversed. What will be the pros? The pros is small file size. Okay. But the con is going to be, it will be less accurate. Chances of error, less accurate. Chances of the error. This is basically what the sampling rate, what exactly the impact of sampling rate is going to be. So everybody got the idea in sampling. Like, this is basically what we talked about. When we pass the analog signal through sampling, we got all these samples, like something like that. And now these samples will feed to quantization. Let's see what is quantization. And after quantization, we will have our final digital and discrete signal. So in quantization, what typically we do? In quantization, we round off the captured point or captured values to nearest quantization level. And very, very important thing about quantization. In quantization, we need to set bit depth. Please remember bit depth. We're going to talk about bit depth in detail in our next coming chapter, but it is very important from quiz point of view. So in quantization is sometimes we also call it bit depth as well. So let's understand what is basically quantization and what are the quantization levels. Okay. So in quantization, let's take the same example. Let's say this is basically the same signal having which is distributed over second. 1, this is 2, this is 3, 4, 5, and let's say 6. Okay, and that's basically our signal. Assume that this is the signal, for example. So what we do is, this is basically the time when it captured, and let's say this is the strength, or let's take it as amplitude or power, amplitude, or let's say puppy's weight, for example. Let's say this is our puppy's weight over 6 months, and this is basically the weight. Okay, so we're gonna actually put the scales here, for example, starting from 5, 10 pound, 20 pound, 30 pound. Okay, so what we have done is, like for example, just assume that without quantization levels. What's the problem? What is the problem? The problem is that, let's say if we are taking one sample, like in each month, you just so you just weigh, you just check the weight of your puppy just monthly, like monthly you're taking the sample. Each month, one time you just measure the weight. So if sampling rate, this is sampling rate, by the way. So let's say one time you are checking the weight of the puppy per month. Okay, so let's say in 1 month you check the weight of puppy, and let's say this is basically the weight of puppy was something like that. Second month you wait, and let's say this is basically what the puppy's weight is. Let's say this is the puppy's weight. In the 5th month, 6 months, that's the puppy's weight. For example, this is what you're doing. We are checking the weight over 6 months. So 1, 2, 3, 4, 5. So we checked 5 times the weight of puppy after the puppy born. Now, what is the weight? What is the value of this particular point? This is what we are doing. Round off the value to the nearest level. So let's say we don't have level. Right now the level is 5. This is the level. 10, 20, 30. That's the level. So what do you think? What would be the value of this particular sample? Since we don't have any level, you will say 4.9, but we didn't define 4.9. So what we do is we will round off to nearest level. This is 5. And now this, what do you think? Is there any level? What do you think? Is there any level? So we just have level 5 and 10. What would be the value of this one? So this is the value. What do you think? It is close to 10. So we will round it off to 10. What about this? It is close to, for example, 20. We'll put it 20. It is close to 20 again, 20. It is close to 30, 30. So since we didn't have more levels to round off, to correlate with, so that's why this is the value. So let me just show you the value, how the value or output will look like after the quantization and sampling. So this is the value 5, like it will start from here, 5. The puppy's weight is 5 pound. Then the weight is 10 pound, like the next month, 10 pound. Then the puppy's weight, 20 pound. Then the puppy weight is again 20 pounds, sorry, because for 2 months it is 20. So it is something like 20 and then 30. So from 1 month, 5 pound. Second month, 10 pound. Third month, it is 20. And again, 4th month, it is 20. And then all the way to 30 for 5th month, and then 6. So this is basically how it looked like, and actually this was basically the graph trend. So the problem is that we had less quantization levels, or you can say bit depth. So if you start increasing more levels, let's say if you put one more level here, let's say this is the value is, assume that this start from 0, so it is, let's say 2.5. It is assumed that 7.5. Assume that it is basically, for example, 10, we should have 15 here, and then 12.5, we should have 17.5 and all that. So if you increase the levels, then what will happen? We have more accuracy. Like this sample will be 5, But now this sample is close to 7.5, not the 10. So this is going to be 7.5. This is going to be more close to 15, not 20. It is 15 now. This level is more close to 20. It is 20. Or, I mean, maybe, of course, it is 25. But I'm 20. This is more close to, for example, 25. Assume that, or 27.5. So it's going to be 27.5. Are you getting a point? So again, we add the quantization levels in order to we put the quantization level so we can round off these captured values which we captured in sampling. So in sampling, we just take the samples, and in quantization, what we do is we round them off to the nearest quantization level. So if we, again, the same logic here, if we increase number of levels, then it will be more accurate. It will be more accurate, but the problem is going to be larger file size. So same pros and cons. If you increase the quantization level, file size will be larger, but it would be more accurate. Just like we talked about the sampling as well. So just to give you a good understanding about it, let me just combine sampling and quantization. For example, let's say this is basically analog wave. We got this analog wave. Let's say this is an analog signal. Assume that this is the analog signal. And let's say it has been captured over time. Let's say this is 0, 1, 2, 3, 4, 5. For example, this is the 5-second instant. And let's say this is the amplitude or power. Let's say again 1, 2, 3, 4, and 5. So assume that this is analog signal and we need to do sampling. And we need to do quantization in order to have the discrete value, quantization. Okay. So now in order to do sampling, what we have to do? In order to do sampling, we need to set a sampling rate. What is sampling rate? Sampling rate it at like how frequently, how often we will take the sample or capture the sample. Let's say we are doing 2 samples per second. So we are doing 2 samples per second. Let's capture the sample. Let me draw this figure again here. Okay, so 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. For example, this is the signal. Similar signal again. So now we need to take samples, 2 samples per second. Let's say this is 1 sample, second sample in 1 second. Again, within this second, 2 sample, 1 sample, 2 sample. It should be on the same time instance. This is 1 sample, second sample. This is just for understanding purposes. Otherwise, it would be exact or accurate samples. 2 samples within this second. So this sample, during these 2 instances, we picked all these samples. This is called sampling. Okay. So now, once we forward the samples to quantization, so quantization will get something like that. Quantization again, 1, 2, 3, 4, 5. Here we got 1, 2, 3, 4, and assume that this is 5. So what we got here, we got 2 samples here. 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 And 2 samples, for example, here. This is what we got in quantization phase. In quantization, assume that, for example, we have 3 levels in 1 second. 3 levels, 3 quantization level per second. So in 1 second, we have 3 levels. Let's say this is start from 0. Let's make it simple. Let's make it easy for us. So let's make it like 2 samples per second, or let's say 2 levels per second. So 2 levels, so we are going to make, we need to break down 0 to 1 into 2 phases. So it is from 0, 0.5 and 1. It's basically one, one level in fact. Otherwise we need to make some more points, and I don't want you to get confused. So 0.5, this is 1.5, 2.5, 3.5, 4.5. If it would be two levels, so then there would be 0.337, 0.67. So that's why I didn't pick those two levels. Three, it would be 3, then it would be 0.3, 0.33, 0.66, and then 0.99 or close to 1. So I didn't want to get you confused, so that's why I assigned one level. Now, what are the levels? This is basically the levels. I'm going to actually make all these levels like this, so you have better understanding. So all these are basically the quantization level. Now we need to round off all these samples to the nearest level. So let's say this sample, what do you think, what would be the value of this sample? The value of this sample is going to be, because it is close to 0.5, it is 0.5. It is basically in the middle, like it could be 0.75, but we don't have 0.75, so it's close to 0.5, so it would be 0.5. Value is exact on 1, so 1. Exact on 1, 1. This value is close to 1.5, 1.5. This is also close to 1.5, 1.5. Value is close to 2, right on to 2. Value is 2.5. This value is close to 3. I'm going to put it 3. So this is basically the discrete signals. We got discrete values 0.5, 0.5, 1, 1, 1.5. All these values are called discrete values. And then we will convert into digital. We will discuss that, of course, in the next coming chapter, coming part. But this is basically sampling and quantization. I hope you guys got the idea how we convert this analog wave. This is having infinite information into this having finite information, having this sample. So although we had discarded some of the sample, but we got most of the information. The last thing for today, again, very important thing, regardless of the signal, like signal could be images, it could be audio, it could be video, but it does have two steps to convert images, video, and audio into a digital format or discrete format is sampling rate and quantization. So regardless of the media, we for digitization, we use sampling and quantization. In images, sampling rate can affect the resolution of an image. We will discuss that. We have chapter number 2, which is based on images, and number of pixels. We will discuss in detail, but this is just for your understanding. So quantization or sampling rate of images affect the number of pixels or resolution. Bit depth defines the colors. So if you increase the bit depth, it will increase the color palette. If you increase the sampling rate, it will increase the pixels of an image, like megapixel cameras and all. Video, again, for sampling rate can affect the pixels of video plus the frames. We will discuss that in our chapter number 4. Bit depth, again, it matters. I mean, it defines the colors. So for example, if you have more bit depth or quantization, it will bring more colors to your video. Audio, it's basically the sampling rate can affect the frequency, or you can call it pitch. And quantization can affect the amplitude. And amplitude is basically the sound volume. Okay. We will discuss that in our class as well. If anybody will have any questions, please do let me know. So in this part, we have mainly discussed two things: difference between analog and digital data, and we also talked about digitization, how we convert the analog signal into digital information. And we discussed that there are two steps: sampling and quantization. We're going to talk about it in our class. If you will have any questions, please do let me know. Thank you.